Here's a run-through of the DVB-S2 standard. This is what we know so far. DVB-S2 stands for Digital Video Broadcasting Satellite Second Generation. There is a recent extension to this standard called DVB-S2X that has very low SNR capabilities and a lot of other goodies. The GEO project, ASCENT, and eventually the High Earth Orbit project are expected to transmit using DVB-S2X. This is the foundation of our Common Air interface. DVB-S2X specifies the modulation and coding for our receive signal. There are 5 major landmarks. 1. An input stream adapter. Input streams can be packetized or continuous from single or multiple sources. This is helpful. 2. Forward error correction. R type is low-density parity check codes concatenated with BCH codes. So what does this mean? A concatenated code is one that combines 2 different coding schemes. In coding theory, there's a fundamental problem in that finding a really good code that has very low probability of error usually means that the block length has to go up, and the decoding is more and more complex. When you use 2 codes together that each have particular strengths, they balance each other out. You can get an exponentially decreasing error probability, but you only have to pay a polynomially increasing cost in terms of code block length. This may seem complicated, but just remember concatenation is codes doing teamwork, and the standard that we're using is badass. Our inner low-density parity check code can achieve extremely low error rates near channel capacity. This means it's about as good as you can get. The outer BCH codes are used to correct sporadic errors made by the low-density parity check decoder, and to trick it out so that we don't have enormous block lengths and stuff like that. 3, we have a wide range of code rates. The code rate is expressed as a fraction. The top number is how many uncoded bits go in. The bottom number is how many coded bits come out. We have 4 constellations. This is the type of transformation from bits to things that we can actually transmit, symbols. We have great choices here, and DVB-S2X provides additional choices. 4, there is a variety of spectral shaping available to us in DVB-S2. This is a really neat thing. You can change the pulse shape of a transmitted waveform in order to make it better suited for the radio environment it's expecting to be traveling through. Usually this means making it fit into a bandwidth better. You don't get something for nothing though, so being too aggressive with the pulse shaping shows up in other aspects. Our particular shaping offers different levels of raised cosine filtering. DVB-S2X provides additional levels of this type of shaping. 5. This standard lets us learn and develop with something very much like cognitive radio. As you can see, there are a lot of choices for coding and modulation, lots of different combinations. We can specify a fixed coding and modulation. This is called CCM, for constant coding and modulation. In the past, people like us would look at a link, design for the worst case solution, and use coding and modulation that would cover all these bases. DVB-S2 has constant coding and modulation, but it also specifies something called variable coding and modulation, or VCM. The coding and modulation can be changed on a frame-by-frame basis in response to different station types or changes in the channel. In addition to that, there's something called adaptive coding and modulation, or ACM, where the modulation and coding automatically adapt. This can happen on a frame-by-frame basis, and there's algorithms. DVB-S2 has something called annexes in the document, sort of like appendices. In Annex M, there's a specification for something we've already talked about wanting to do. We want to map the transmitted services or station streams into time slices and then be able to recover information without having to demodulate the entire signal. DVB-S2 follows the usual flow of having input data coded up to remove unnecessary redundancy, which is called source coding, and then it is put into one of 2 different stream types. Because DVB-S2 is designed for MPEG streams, it has a lot of mechanisms for MPEG data types and streams, and I believe that this is the transport stream path in the drawing. We aren't going to use MPEG, so we fall into the generic stream category. The functional blocks of DVB-S2 include these things in parallelograms. Mode adaptation, which starts to build up the data frames by constructing the right header to go with the data. Stream adaptation, which adds in the right amount of padding and scrambling. forward error correction, which produces coded frames that are of one of two sizes. The difference between the channel coding here and the source coding that I mentioned earlier is source coding removes redundancy that's not needed, and forward error correction adds the right type of redundancy in order to make your data really durable as it's transmitted. Mapping to constellations, which is the modulation, is the next block. And finally, there is physical layer framing. An open question that immediately occurred to us is how minimal of a station can be supported? And the answer is probably going to be in the specification dealing with the physical layer framing, or part of the answer. Driving it down as low as possible is going to be fun and challenging. What we're anticipating is that the space teams will obtain an implementation of a DVB-S2X transmitter. Talks are already underway for this. Phase 4 ground is going to engineer the various DVB-S2X receivers. Standard documents are already in the repository, and work is beginning, so get off the bench and hit the books. So let's talk a bit about some changes in the uplink for Phase 4 radios. We were MSK, or minimum shift keying, but we are now OQPSK, or offset quadrature phase shift keying. That is what the payload team is currently designing for. Like MSK, offset QPSK has no more than a 90-degree phase shift at a time. This is good. In order to create this, you begin with a QPSK signal, where you take 2 data bits at a time. These 2 binary data bits make 4 distinct values. Each of these values are mapped onto 4 transmit phase shifts. For offset QPSK, the odd and even bits coming into the modulator have a timing offset of 1 bit period, hence the name. That means the in-phase and quadrature signals, the I and the Q, never change at the same time. The power spectral density of QPSK and offset QPSK is the same. The shift in time doesn't affect that. Uplink experiments are beginning. We started putting together a team HackRF, which will investigate the use of HackRF SDRs as one of the Phase 4 radio recipes. Lots of other experiments to work out other recipes for amateurs to experiment with need to happen too. If you have a set of hardware and you want to work in parallel, then speak up. The USERPs will get into the act ASAP, some people have Blade RFs, and so on.